So, hello, ladies and gentlemen. I'm here with you again. Let's start. Today is our last lecture of the course software system design. As you see, I gave this lecture a kind of composite number, 11B and 12 at the same time. The idea is that I have joined together three patterns by some reason. I will explain you the reason later. So therefore, anyway, this is the last lecture. Okay, let's start. My first slide is a standard one. I always put it at the very beginning of the lecture. It gives a kind of the overall view at what is the whole topic, design pattern. As you see, and as you already understand, that design pattern is a kind of scheme for organizing classes, objects, and methods appropriately to solve a particular problem. My presentation, again, is built on the same metrics, I would say. I try to describe you a problem, to present you a problem, and then I just discuss a way to solve that problem using a particular pattern. So this is why I put this reminder to any lecture. Here is the overall taxonomy, also the standard slide. Overall taxonomy of design patterns presented or described in the book of Eric Gamma. We have already considered some of them, as well as you have considered some others during your labs. And today we will consider three patterns: interpreter, iterator, and visitor. There are some reasons why I have collected them together. We will see that very soon. So these are formal definitions of these patterns. I would just skip this slide for the moment because we will consider them in more detail later. These definitions are taken again from the book of Eric Gamma, classical book of Eric Gamma and his colleagues. Why we consider these patterns together? Because of the very obvious reason. They all typically deal with a similar or just same basic hierarchical structure. This is the reason. Another reason is that all the patterns exploit the same pattern we have already considered before. We will see that when I come closer to these patterns. So 2 points. All these patterns deal with the same complex structure, hierarchical or graph-like structure, or any complex structure. And the second reason is that they exploit the same pattern from our list. The pattern they are based on is composite. And my intention is to present you, to remind you some slides from one of our previous lectures that was devoted to composite. Before we come closer to the three patterns that I have chosen for today. So, composite pattern. It answers the question how to work with atomic and composite objects uniformly. This is the idea behind composite pattern. This is very practical aspects because in real life and in real programming as well, we deal with two base categories of objects. They can be characterized as atomic and composite objects. Atomic objects or terminal objects are just the entities that do not have an internal composition. They do not contain other objects, I would say. Whereas composite objects are typically contain a number of sub-objects, or however you call it. Here is the slide from the lecture number 6 with the examples in various areas: graphics, type system, cooking, etc. I would give you some more examples later. Okay, so this pattern will be actively used for explaining these three patterns: interpreter, visitor, and iterator. Okay, so this is the composition that I'm going to remind you. Our common approach for unifying the access to both categories of objects is to define a unified interface for all elements, starting from the very base one component. Well, look at the next slide. Again, this is an example of the implementation of this pattern, composite. Look carefully at what is drawn on this slide. First of all, we have defined the base class. We called it component. There are three pure virtual functions. I have chosen C++ for this pattern and for all other patterns today. So, three pure virtual functions, get, add, and remove, that compose a common interface that will be used by all categories of objects. And two derived classes, composite and leaf. They represent composite objects and terminal objects respectively. Look at the leaf class. It represents any kind of terminal object that doesn't have own object, doesn't own objects, other objects, and it provides its own implementation for get, add, and remove. This implementation is quite trivial. Get, for example, just returns the object itself, whereas add and remove have empty actions. They actually do nothing, just because we cannot add a new object to the leaf, as well as we cannot remove an object because there are no objects. For the same, the implementation of the same interface in composite is, of course, more complicated, and it is based on the internal representation of a composite object. In my example, composite object is implemented as a list. I use the standard list class from the C++ standard library. And of course, get, set, add, and remove would deal with this internal representation. We are not interested in the details of such a representation. Now, I'm going to present you the idea, or I have already presented you the idea behind composite pattern. So again, the idea is to somehow provide the unified interface for both categories of objects. So again, why I remind you about this pattern? Just because I will be using it when I discuss our three patterns selected for today. Okay, before we come closer to our target patterns, I would like you to discuss a little bit or think a little bit about hierarchy or any composite data structure from the real world. And the first obvious example is a company, an organization or a company. It is quite obvious that the data structure describing such an entity as a company is tree-like. Each company, each organization has some number of departments. You can think about in a policy university as an example. Departments are divided in laboratories, in groups. And finally, there are terminal objects in any company that are employees or collaborators. And the structure of any organization very adequately represented as a tree-like structure. Two next examples are closer to our IT area. Algorithm. Look, think about any algorithm that consists in some number of steps or actions. We can see different kind of actions in any algorithm, starting from simple actions. If we think about a program in a programming language, which is actually an algorithm, we can see so-called simple actions, something like assignment. Assignment is a kind of elementary action. It can be considered as an example of a terminal class, or an object of a terminal class. At the same time, there are composite steps or actions in any algorithm. These are sequential, conditional, and repetitive actions. I don't need to explain you what are such actions in any programming language. So the main conclusion here is that such a kind of non-material thing as algorithm also can be represented as a tree-like data structure. By the way, if we consider some other aspects of an algorithm, for example, data flow, we will come to an idea of a graph describing such data flow. Okay, two more examples. Integrated development environment, the thing you are working with every day. It is also can be considered as a composite structure containing windows of different kinds, bars, menus, buttons, etc., etc. Any text editor, in turn, as a part of an IDE, also is a composite object. And one more interesting example, a language type system. As you know very well, each language includes the notion of type. And typically, each language has a variety of different types. Those types are classified somehow, and they also compose a structure. For example, in C++ or in any other language, we have fundamental or predefined types like integers and floats, and compound types or derived types in some other languages, user-defined types that are composed from components of other types. And the last example in this list is abstract syntax tree. If you do not know for sure what does abstract syntax tree mean, I would just tell you that this is a very typical notion in the area of compilation, in the area of developing compilers. The idea is that a language, a program written in a programming language, being processed by a compiler, is represented internally within the compiler as an abstract syntax tree. In accordance with the syntax of the source language, the program written in that language is represented as a tree-like structure, where nodes of that structure represent various constructs, various language constructs. And those constructs can also be either terminal, such as identifiers, parentheses, commas, or constants, as well as composite notions like any language construct, compound, conditional, etc., etc. Okay, I have specially marked the last example of this list because I'm going to take this example for the further considerations. Let's go to the next slide. The first pattern from the list of three, interpreter. Here is the formal definition of that notion taken from the book of Erich Gallner. Interpreter. Given a language, the pattern defines a representation for its grammar, along with an interpreter that uses the representation to interpret sentences in that language. What is to interpret sentences? It depends on our aims. We will see that in details later on the example. By my opinion, I'm not going, I have nothing against such a definition. However, by my opinion, this definition is a little bit narrow. It's just about one kind of use of the interpreter pattern. I would take the responsibility to give you a more general and at the same time more simple definition of the pattern. The pattern interpreter performs an algorithm on a hierarchical structure. This is the idea. This is the idea. Not necessarily the language is the subject for this pattern, grammar, etc. But any algorithm, pattern interpreter, it performs an algorithm on any hierarchy, any algorithm on any hierarchical structure or any complex structure. Below are some examples of these things: structure and algorithm. Look at this table. If we have a company, if we consider a company as a structure, the appropriate algorithm could be just print the structure of the company. We try to apply a printing algorithm to the structure representing a company. The same is about IDE. If we have an IDE, if we are implementing an IDE, we would need to, from time to time, to redraw the current state of that IDE on the screen. And coming back to our favorite example about AST, Abstract Syntax Tree, we can imagine an algorithm calculating the value of an expression represented as AST. I'm sure you quite understand this quite clearly. An expression is represented as a tree, and our aim, suppose the aim of the algorithm is to calculate the value of that expression. We will just see that. I have marked it by the arrow. We will see that on the example. Okay, so what is the example? Look at the task description I have presented on this slide. Suppose there is a formal grammar that defines a syntax of Boolean expression. You understand quite clearly what such a formal grammar represents. There are different elements in any Boolean expression. First of all, there are operands. Operands are variables, constants, that is true or false, and there are operators on such operands. Operators are logical and, logical or, logical negation. And we also use parentheses to group some sub-expressions together. Okay, so the second point, there is an abstract syntax tree that corresponds to the grammar that is built in accordance to the grammar and represents some concrete expression. Suppose we have a concrete expression and have represented as an abstract syntax tree. And the whole task is to implement the algorithm that evaluates the expression. Look at the next slide. Here are some concrete pictures on that. First, the grammar, the formal grammar describing the structure of Boolean expressions. Everything is completely clear. I use so-called BNF notation, Backus-Naur form, for writing the grammar. You absolutely understand. The grammar consists of 6 productions. Each production has the left part, which is the name of the corresponding non-terminal rule of production, the name of the production, whereas the right part describes the structure of that production. For example, let's take N and exp production. It says explicitly that any and exp construct consists of 3 elements. The first element is a Boolean expression. The second element is AND operator sign. AND is an operator sign or keyword. And the third component is again Boolean expression. By the way, the semantics of such a production should be again clear to you. We take 2 operands that are Boolean expressions and apply an logical AND operator on them. Looking at the first production, the kind of root production for the whole grammar, it just explains what is Boolean expression. There are several options separated by vertical columns. Options are variable, a kind of variable, constant in this example is true or false, that is described on the 5th rule, or expression, or AND expression, or not expression, or the sequence of 3 elements, 2 parentheses enclosing the Boolean expression. So, for our purposes, we just define variable as one of the name represented as a single character. Okay, I'm not going to waste time describing you the details. I suspect that you understand that quite clearly. The second element of our task, the concrete expression, built following these rules, these grammar rules. Again, the idea of this concrete expression is quite clear to you. I'm sure you understand what is written. Different languages has the same or very similar rules for writing logical expressions. Well, here I use keywords for denoting operators. However, you can use just any other characters that, for example, defined in C or C++ or in similar languages. And what is the third element of our task description? The tree. The abstract syntax tree that corresponds to this expression example looks like as follows. Look again. I expect that no new for you on this picture. This is a tree-like structure where a hierarchy of nodes represent the corresponding elements of the source expression. There are operators and, or, and not, and the operands. Operands are represented as variables. Okay, let's go on with this task. And now we come closer to the idea of interpreter pattern. Let me remind you that our task is taking, I come to the previous slide, taking these things as preconditions, write an algorithm that would calculate the value of the expression. Of course, we assume, there are some assumptions on this task. We assume that someone has already built such a tree. So we deal with the tree generated by someone or by some program. We assume that all terminal nodes like operands A, B, C, and D already have some values. So these are the assumptions taken not to consider related things that are not related to our pattern. So we assume that everything is ready for us to solve the task. That is to build the algorithm, calculate or evaluating the value of such an expression. So what is the approach? For each terminal and non-terminal symbol from the grammar, we define the corresponding class. We define classes for non-terminal symbols. We define classes for terminal symbols. Non-terminal classes are derived from composite. Terminal classes are derived from leaf. Keep in mind the composite pattern we have considered before. And we add virtual evaluate function to root class and override it for each derived class. I have made a small grammatic bug in the last bullet. Look at the code. This is a part of the implementation, only part because I'm not going to present you the whole list of classes. So look, I have taken, let's look back to the previous slide. Here we have the root production, Boolean X. It represents the overall structure of the whole Boolean expression. And we have created we have defined the corresponding class Boolean X. It is a composite class, of course. It contains some other objects as components. And therefore, we have derived it from composite. Okay? Look at the body of the class. There is the only element, the only member of that class that is pure virtual function evaluate. Okay? The second class is the example of terminal class. I've called it operand. Operand means either constant or variable. Therefore, it cannot contain other objects as part. Look at what is written here. First of all, I have derived it from the leaf class. Remember the composite pattern. And I also defined pure virtual function evaluate within it. And one additional member, value, which is of type Boolean. The idea is that each operand, being it a variable or a constant, has a value. So therefore, the configuration of the operand class is as it is presented here. Okay, let's go on. So again, we have defined classes for each terminal and non-terminal element of the source grammar. Okay, here are some final classes from the whole hierarchy. Look, or exp. Look, the first class, or exp. Let's quickly come back to our grammar. Look at the first rule. By definition, or exp is the case for Boolean exp. That is, or exp is actually a Boolean exp. Or expression is a Boolean expression. Our class declaration here directly reflects this aspect. Or exp class is derived from Boolean exp. Look at the previous slide. Boolean exp has the pure virtual function. Therefore, any class derived from it should implement it. Here is the implementation. Here I provided implementation of the evaluate function in or exp class. Look at the body. Look at that implementation. What did I write here? I have emphasized this by red color. What does it do? By definition, and again, keeping in mind the structure of composite class from composite pattern, This class contains at least two elements, or exactly two elements, two operands. Therefore, what I do, I delegate evaluating of the child sub-expressions to the corresponding evaluate function. And I perform get functions. Get functions just implement access to corresponding child element. And I apply evaluate to all these childs, assuming that get, the first call to get returns as the reference to the first element, whereas the second call to get gives us the reference to the second element. This is my assumption for simplicity, because I'm not going to go into all details. It is more important to demonstrate you the idea. So what do I do? How did I implement evaluate for OR exp? I delegate calculating values of elements to the corresponding evaluate function. Notice that the evaluate function must exist, the real implementation must exist in all derived classes. Therefore, I just calculate the value of operands and apply logical OR operator. In C++, this logical OR operator is represented by two columns. Apply it and return the result. So the result of the whole OR expression, of calculating OR expression, is the result of calculating its operands and applying logical AND to them. Exactly the same is about AND exp. The difference is that I apply logical AND operator to the values of operands. Okay, let's go on. Here is the continuation of my implementation. Look, not a negative negation is represented by the class not x, and here I also must implement evaluate as well as all other derived classes, and here is the implementation. Very simple one. Look at variable. I have defined class variable, which is a kind of operand. It contains two elements. Excuse me. It contains the name. Well, this is for completeness. I don't need this name actually. All I need is the value, and the value was declared in the base class operand. So all the evaluate implementation for variable does is just returning the current value without any problem. And I didn't provide the implementation of constant class. It is also derived from operand as well as variable. The only difference between constant and variable is that constant doesn't have a name, because this is an unnamed entity, just true or false. Okay, so defining the pure virtual evaluate function in the base class, we have overloaded this function in all derived classes. Okay, this is the explanation. I have already given you all explanations, but this is just to repeat and to keep you informed about the details. Well, again, I refer to the implementation of composite class. There is the get function defined there. It returns the reference to a component. And the assumption, as I have already told you, my assumption is that the first get gives you the reference to the first child, and the second call to get gives you the reference to the second one. This is just my assumption, again, for simplicity. Okay, so again, all we did is that we have defined versions of evaluate function, uh, defined or implementations of evaluate function for all classes derived from Boolean exp. And here is the example of how this the whole situation, the whole composition works. Look, here I create a new object of class Boolean exp. I don't care about how exactly this the argument of this Boolean exp is processed. Again, we assume that someone has already built a tree for us, and our responsibility is just to traverse the tree, as I shown on the previous slide, and calculate the result. So, having a tree, which is expression in my example, we just apply evaluate function to that. And using the standard mechanism of polymorphism or virtual functions, which exists in any object-oriented language, we get finally we get the result. We have the value calculated for the whole logical expression. Again, we are not care about who and how such a tree was who built the tree and how it was built. Here are some assumptions. Of course, this my presentation is just give you the idea behind interpreter. Here, interpreter is the calculator or evaluator of the value of expression. The assumptions, as I have already told you, are that we don't care about how AST was generated, and we expect that it was generated correctly. That is, binary operators like and or have exactly 2 children, and not, which is unary operator, has exactly one kid. Okay, that's it about interpreter. This is relatively easy but very impressive pattern, by my opinion. We just especially elegant the last declaration of result looks especially elegant. We just apply evaluate to an expression, getting the result. And evaluate goes or execution goes along the whole tree, calculate applying evaluate the corresponding versions of evaluate to each subtree, and getting the cumulative result. This looks quite elegant. Okay, that's it about interpreter pattern. Now let me make a break before we come to iterator and visitor. So, break right now. I stop the demonstration for some time.